13.8 billion years ago, every galaxy, every star, every atom in your body was compressed into a space smaller than a pinpoint, hotter than anything that has existed since. That was the birth of the universe. From that single blinding instant to the 100 billion galaxies we observe today, something extraordinary had to happen. The first clue is written in the oldest light ever detected. At the absolute beginning, space, time, and matter did not exist inside a pre-existing void. They were bound together, locked within an unimaginably dense, compact point of pure energy. A fraction of a second after this opening moment, the young cosmos underwent a sudden, extreme expansion known as inflation. In less than a trillionth of a second, space itself stretched at a rate far exceeding the speed of light. This rapid ballooning smoothed out the fabric of the universe, expanding it from a subatomic speck to a vast, nearly uniform expanse in an instant. What remained after this brief epoch was a nearly featureless ocean of hot, glowing radiation. There were no stars, no planets, and no physical structures of any kind. The infant universe was almost perfectly smooth, possessing only microscopic, random fluctuations in density. This extreme uniformity poses the central mystery of cosmic history. How does a universe starting in such absolute hot simplicity evolve over 13.8 billion years into the highly organized cosmos we inhabit today? The journey from a featureless fog of energy to a complex cosmic web is a story of continuous, massive transformation across deep time. The answers lie in how those tiny primordial density ripples began to pull together, setting off a chain reaction of physical processes that would eventually shape the entire observable universe. For nearly 380,000 years, the universe remained a dense, opaque plasma of trapped light and charged particles. Energetic electrons and protons collided constantly, scattering photons like headlights in a heavy fog. But as the expansion of space stretched and cooled the primordial soup, temperatures plummeted to around 3,000 Kelvin. At this threshold, electrons finally bonded with protons to form the first stable neutral hydrogen atoms. This transition, known as recombination, changed everything. With electrons locked in orbit, the cosmic fog cleared, and the trapped light was suddenly released to travel freely across the cosmos for the first time. Today, 13.8 billion years later, this primordial light still bathes the entire universe. Stretched by the ongoing expansion of space into the microwave spectrum, it exists as a faint, uniform glow of radiation at just 2.725 Kelvin. This cosmic microwave background is the oldest observable fossil in existence. It provides a direct, measurable snapshot of the infant universe. While nearly uniform, the afterglow contains micro variations in temperature, measuring just fractions of a degree. These tiny fluctuations represent areas of slightly higher and lower density. They are the primary blueprint for all cosmic architecture. Within these subtle ripples lay the seeds of gravity, destined to pull matter together into the massive structures of the modern cosmos. For millions of years after the release of the cosmic microwave background, the universe remained dark and cold, a vast expanse of hydrogen and helium gas. But gravity was at work, pulling these pristine gases into increasingly dense pockets over immense periods of time. Eventually, these pockets collapsed under their own weight, raising core temperatures to millions of degrees and igniting the very first stars. Known as Population 3 stars, these colossal, short-lived giants were completely metal-free, composed entirely of the primordial elements born in the Big Bang. They burned incredibly hot and bright, bringing a sudden end to the cosmic dark ages. Inside these stellar furnaces, a new process began. Stellar nucleosynthesis fused simple hydrogen and helium atoms into heavier elements, including carbon, oxygen, and iron. These stars became the first elemental factories of the cosmos. When these massive stars exhausted their fuel, they died in violent supernova explosions. These supernova blasts scattered the newly forged elements deep into space, seeding the surrounding gas clouds with the raw materials of complexity. This stellar seeding transformed the universe from a simple, two-element void into a chemically rich environment. Every atom of iron in our blood, oxygen in our air, and carbon in our cells was forged inside these ancient stellar crucibles. Without this first generation of cosmic makers, the universe would have remained a sterile expanse, completely incapable of forming planets, rocky worlds, or the chemistry of life itself. As these newly forged elements drifted through space, they fell under the control of a massive, unseen architect. Gravity needed a physical template to build a highly organized universe. This template came from dark matter, an invisible scaffolding that does not emit, absorb, or reflect light. Its immense gravitational pull acted as the primary cosmic anchor. In the early universe, dark matter clumped into vast spherical halos and long interconnected filaments. As ordinary gas and heavy elements drifted into these massive gravitational traps, they pulled inside the dark matter wells. Under this relentless pull, the gas collapsed, igniting the star clusters that would form the first galaxies. These infant galaxies did not remain isolated. Drawn along the invisible dark matter highways, they collided and merged, building larger stellar systems over time. Supercomputer simulations show that this continuous process of accretion and merging constructed the vast, web-like network of the modern cosmos, organizing matter on the largest scale possible. Astronomers confirm this simulated structure by measuring how light travels across the expanding cosmos. As light from distant galaxies travels toward Earth, the very fabric of space stretches. This stretching elongates the light waves, shifting them toward the red end of the spectrum, a phenomenon called redshift. By measuring this redshift, scientists can calculate exactly how fast a galaxy is moving away and how far it has traveled. Collaborative projects like the Sloan Digital Sky Survey have measured the redshift of millions of galaxies, converting flat images of the night sky into a precise, three-dimensional map. These massive surveys reveal that the universe is not a chaotic scatter of stars. Instead, galaxies cluster along giant, interconnected filaments, leaving vast cosmic voids between them. This mapped reality perfectly matches the simulated cosmic web, turning the night sky into a physical archive of cosmic history. Today, 13.8 billion years after that silent opening second, the observable universe contains hundreds of billions of galaxies. Each of these massive stellar systems, bound together by invisible dark matter, contains billions of stars, planets, and chemical elements forged in ancient stellar cores. This modern cosmic web, spanning billions of light years, is the result of a long chain of physical transformation, stretching from a hot, dense beginning through the release of the first free light to the birth of the earliest stars and the growth of massive cosmic structures. But the cosmos is not finished. It is still changing, and its expansion is accelerating. A mysterious force known as dark energy acts against gravity on the largest scales, pulling galaxies farther apart and determining the future shape of the entire cosmic structure. Inside this vast, active expanse, stars continue to form, burn, and die, while planets orbit in the quiet corners of mature galaxies. Our own planet and the life upon it arrived very late in this immense history. appearing only in the last fraction of cosmic time. We exist as part of an ancient, changing system that is still expanding and still tracing the physical laws set in motion at the very beginning of time. Today, the cosmos continues its silent expansion, carrying the secrets of its birth into the deep future. We are not mere spectators of this cosmic evolution. We are its living legacy, looking back at our own origin. Subscribe to join us as we explore more cosmic mysteries.